So once we have a candidate solution for a recurrence relation, we can do a quick check like the one we did before in the guess and check method. That's a pretty reasonable way to kind of see that we're on the right track. We also, however, might need to actually write a formal proof that a candidate formula we have solves a recurrence relation. And for that, we are going to usually need our good friend mathematical induction. So let's go ahead and jump right into an example of using induction to prove a solution to a recurrence relation. So here we are. Here's a theorem that we'll prove. Let a sub n plus 1 be equal to 4 times a sub n minus 3 with initial condition a naught equal to 2. So this is a recursive definition of a sequence where in order to get the next element of the sequence, I'm going to take the previous element, multiply it by 4, and subtract 3. And what we're going to show is that we have a formula for the sequence given by a sub n equal 4n plus 1. Now, why is this an induction problem? The thing that we need to recognize is that this statement that this formula describing the nth term of the sequence A is true as a description of the sequence defined by this recurrence relation. That formula is actually my P of n, my proposition depending on n that I want to prove with induction. So what I need to do is show that this relation, this formula here, satisfies this recurrence relation for all n, and I'm going to do that with a base case and an inductive step in the standard proof by weak induction. So here we go. Let's do a proof. Okay, so our proof is going to be by induction. So for the base case, what do we need to show about this formula in the base case? We just need to show that this formula gives us the right initial condition. So for the base case, we are going to check n equals 0. And that means that we're going to check to say, hey, a naught, according to our formula, is equal to, let's check here, 4 raised to the 0 power plus 1. Anything raised to the 0 power is equal to 1. So we have 1 plus 1 equals 2. And that agrees with the initial condition. Great, did the base case. Okay, so now let's do the inductive step. For the inductive step, I'm going to suppose that P of k is true, and here, remember, P of k is this statement. So I'm going to suppose that a sub k is equal to 4 raised to the kth power plus 1 for some k. Then to just set up my scaffolding here, we'll prove that, hey, it's also the case that a of k plus 1 equals 4 to the k plus 1th power plus 1 under this hypothesis. So our inductive hypothesis is right here, and I'm going to label it because we're going to use it in a moment. So let's calculate, and this calculation now is going to be very similar to the informal guess and check calculation that we did before. We're just going to take a little time and justify our steps. So let's calculate a sub k plus 1. So the first thing that we need to do here is we need to use the definition of the recurrence relation that we're given. So we know that this is true. And so what we're going to do first is we're going to use that. So this recurrence relation says in order to calculate a sub k plus 1, we need to look at the expression for a sub n, or for a sub k, minus 3. So that's the recurrence relation that we were given. Okay, now what we've done is a really standard induction thing because we want to know something about a sub k, or a sub k plus 1, and we've simplified it into something that involves a sub k using a tool. And so now we are going to use our inductive hypothesis on a sub k, because our inductive hypothesis says that a sub k is 4 raised to the power k plus 1. So here we can substitute 4 raised to the power k plus 1 for a sub k, and then we get a minus 3 here. So that's the inductive hypothesis that allows us to do that. And now if I just simplify with algebra, okay, I'm going to get 4 to the k plus 1 plus 4 minus 3, which is equal to 4 to the power k plus 1 plus 1. And indeed, that's the thing that I wanted to prove. So I'm done. So I'm just going to write as was to be shown. And a little proof square here. So the flow of a proof of a recurrence relation by induction. First, we check the base case. If we have a formula here we want to check, we check that this formula gives us the right base case. And here that means the right initial condition. And then in the inductive step, what we do is we state the inductive hypothesis and what we want to prove. And then we look at the k plus 1 element, so the thing that we want to prove something about. We look at that. We use the recurrence relation that we're given. In our case, it looked like this. We use that recurrence relation to simplify this object down into something involving a sub k, or possibly previous values of a as well. And then once we have a sub k in our hands, we're ready to use the inductive hypothesis and then simplify using algebra. This is a very common workflow for proving that a formula like this one solves a recurrence relation like this one. And we'll see this pattern several more times.